Now we'd like to look at a slightly more complicated circuit, which is what we call a multi-loop circuit. Suppose we have an EMF, and we have a resistor R1, we have a resistor R2, and we have another resistor R3. Now, to make this a little bit more complicated, I'm going to put a second seat of EMF in. I'm going to call this one E1 and this one E2. And I like to analyze this circuit. Now, we're going to use the same ideas that we've done before. Notice we have two junction points. And so first we assign currents in the branches. I'll call this one I1. I'll call this one I2 and I3. And here we have a very simple example of current conservation, that the current that comes into a junction is equal to the current that goes out. Now notice we have two junction points. And the current that's coming into this junction point, you can call this A and B. The current coming in is I2 plus I3, and the current going out is I1. So we have actually the same equation, which is a general rule that if you have n junction points, you have only n minus 1 independent current conservation equations. Now, the next thing we want to do is we have loops. And so let's do some circulation. So we have a circulation direction here. And I'm intentionally going to choose a circulation direction the opposite way there. And I have two loops. And so I want to do Kirchhoff's law of the sum of the voltages around a loop is 0. So we start to write them out. We cross the battery from the negative to the positive terminal, so we have plus E1. We're crossing the resistor in the direction of the current, minus I1 R1. We're crossing resistor 2 in the direction of the current, R2. That's our first equation. And our next equation is, let's start at any point. So let's start at point B. Notice that we're crossing resistor 2 opposite the direction of current 2. So that's plus I2 R2. Now we're following this branch of the circuit, and we're crossing resistor R3 in the direction of the current. So that's minus I3 R3. And now we're crossing this seat of EMF from the positive to the negative terminal. So we have minus E2 equals 0. And these are our circuit equations. Notice that in this problem we have three unknowns, which is often the case. I1, I2, and I3 are the unknown currents in the branches. And in general, in circuits, we're building a circuit so we know the EMFs and the resistance. We have three equations and three unknowns, and we can solve that algebraically. Now, you might have asked an interesting question. There's actually a third loop in this circuit, a loop going all the way around the whole circuit. Why didn't we include that? Well, let's write that equation out just to see. So in the outer loop, we have plus E1, cross resistor R1 in the direction of the current, cross resistor R3 in the direction of the current, opposite the charge, so that's minus E2, and that brings us back to where we started. So is that a new equation? Four independent equations? It's not. Because let's look conceptually at what we did. When we crossed this resistor, we crossed in this direction. When we went this way, we crossed in the opposite direction. So those have two signs. So if I added my two circuit equations, I'm essentially canceling this leg. Now let's just add equations 2 and 3. And what do we get? We get E1. We get minus I1. Here's where we're canceling the inner two pieces. And so if you add these two equations together, they cancel. We get the minus I3, and we get the minus E2. And that shows our second important idea about circuits, that if we have n loops, then there's only n minus 1 independent equations in this type of topology. And let's just remind ourselves that if we had n junctions, there's only n minus 1 independent current conservation equations, current conservation equations. And these are the sum of delta VI equals 0. And that's how we handle a multi-loop circuit. Now, I want to say one last thing when solving multi-loop circuit problems. We have three equations. There's many ways to solve algebraic equations. When I look at this system of equations, I like to choose one equation as a backbone. This one, I1 equals I2 plus I3. And the reason I choose that as a backbone is I see that in this equation, I can solve for I1 in terms of I2, so I can make a substitution for I1. And in this equation, I can solve for I3 in terms of I2, and I can make that substitution for I3, and then I can solve for I2.